Okay, so now that we have seen three proofs of the Sylow's theorem, we now know very well that any finite group whose order is divisible by some prime p, say, has a p Sylow subgroup. So the next natural question to ask is for some relationship among those p Sylow subgroups, can we say how two of them are related? So this theorem, this next theorem is about them. Well, you won't see the term p Sylow subgroup in the actual statement of the theorem, but it's just about that. You can see the statement. Here G is a finite group and P is a prime such that the nth power of P divides the order of G, but the next higher power does not divide. So that means this is the largest power of P dividing the order of G. Then any two subgroups of G of this order are conjugate. That means any two p Sylow subgroups must be conjugate to each other. That is the claim. So let us now see the proof. And in this proof we are again going to use double cosets. So we start the proof by considering two p Sylow subgroups. Let B two p Sylow subgroups of G. Then both of them have order p to the power n. Now what we are going to do, we are going to see the double coset decomposition of G by these two subgroups. Consider the double coset decomposition of G by A and B, that is this. Where you know that this X varies over a set of representative elements where one element is taken from each distinct double coset. Okay, that's how the union goes. Now we concentrate on the number of elements in each double coset. Note that for which we already have a formula from a previous result. We have seen that in the previous video, that this number is equal to this quotient A intersection XB X inverse. Okay. Now our aim is to prove what? That A is a conjugate of B, which means that we want to prove that A is equal to XB X inverse for some element X in the group G. Suppose that is not true, then we are going to seek a contradiction from such a supposition. So that means we are now going to suppose that A is not equal to XB X inverse for all X. For any X in G, these two are distinct. Well, I can use this space now. Suppose that A is not equal to XB X inverse for all elements x in G. Now note that this intersection is a subgroup of A. So by Lagrange's theorem, its order should divide the order of A, which is p to the power n. So that means this order that you see in the denominator should itself be a power of p, say p to the power m, where the exponent m is at most n because it has to divide. However, due to this extra supposition that m actually has to be less than n. Let me first write that and then we will try to understand why exactly that is so. Then the order, how am I writing this? The order of this intersection is equal to this for some m less than n. But why exactly? Exactly why are we, why do we have to suppose m to be less than n? That's because if you see, if you take m to be equal to n, then what happens? We already know that m has to be less than or equal to n due to that divisibility property that this order has to divide this. M cannot exceed n, that much we know. Now if m is equal to n, then you have this but we already know that this is a subset of this. Okay. Now if in that situation they are they have the same order, and that means they are finite also, then they have to be equal. But then this intersection being equal to A means that A is a subset of XB, X inverse. Okay. Now how many elements are there in A? P to the power n. And how many elements are there in XB, X inverse? We know from a previous result that this is the same as the number of elements in B, which is also p to the power n. So now you are looking at two finite sets A and XB, X inverse, which have the same number of elements. So they have to be equal. And that goes against this supposition. So that's why under this supposition we cannot have equality, and that is why we are taking m less than n. It may look like something not really straightforward, but if you get used to this kind of thinking, then yes, it is straightforward. You think like this 2 or 3 times. After writing something like this, it will automatically come to you that m has to be less than n. Okay, so now this is the situation. Now let us see where this leads us. Now because we can say something about this. Something about this means we know what this order is, or at least how it should look. But we also know the numerator. So we can now write so you can see that we can write it as 2n minus m. And this 2n minus m, I could have, here itself I could have written it like this. So do you see what this inequality is telling us about this? That this n minus m is a positive integer. So the least value it will have is 1, or it may be higher also. In any case, this implies that we will get the factor of p to the power n plus 1 at least in this number itself. That is why p to the power n plus 1 divides this or the order of axb. So that means this extra supposition now implies that p to the power n plus 1 divides all the orders of those double cosets. Hence, from this decomposition, we are of course going to get this equation because this decomposition is a union of disjoint sets, so that's why we get summation. And this then implies that p to the power n plus 1 then has to divide the order of g, which is a contradiction. It contradicts the hypothesis which is there in the statement itself. And that is why this supposition is wrong. So you can clearly see that this is almost like what we did in the previous video. When we needed double cosets for the first time, this is how we argued, and the same kind of argument is working here also. So our supposition is wrong, i.e. we must have a equal to, if you want you can use x here, the author has used g, I think, if I am remembering correctly, for some g in b. So that's how we have the proof of this result. Okay, now next comes the actual number of such p-Sylow subgroups for a fixed prime p of a given finite group G. And there is a lemma which gives us the exact number. The proof of the lemma, however, is not there in the text. Instead, a hint is given. But we will see the proof not here, but in the exercises in the community section. So let me just state the lemma. The lemma number is 212, so it is the sixth lemma. Let G be a finite group and P be a prime dividing the order. Okay, but just hold on. Do we really need division? No, nothing like that is mentioned here specifically. So let me just, in fact, this is not how the statement starts in the text. The text statement just simply goes like this: the number of p Sylow subgroups in G is this and this. But anyway, because we have started it this way, so let me not change this much. Instead, I won't mention whether P divides the order of G or not. If P does not divide the order of G, then also there is a p Sylow subgroup. Okay, let us, before it gets confusing, suppose, let me just make this clear at least. Suppose P is a prime which does not divide the order of G. Then in this situation, what is the largest power of P that divides the order of G? It is this, because this is 1 and this actually divides the order of G, no matter what this order is. Now, is there a p Sylow subgroup? That means a subgroup of this order in G. Yes, it is the trivial group. So we need not actually have always that P has to divide the order of G. This case is also included. Okay, whatever the case is, G is a finite group and P is a prime. The number of p Sylow subgroups of G is equal to this. An index of what? It's the index of the normalizer of capital P, where capital P, we are going to now say what capital P is. Capital P is a p Sylow subgroup, any p Sylow subgroup in fact. This, where P is any p Sylow subgroup. You can see clearly that this number itself does not depend on our choice of P. That's because all the p Sylow subgroups are going to have the same order, and their normalizers also are going to have the same order. So that's why the index is going to be the same, and in particular this number divides the order of G. The number itself, just from the look of it, you can see that this will be a divisor of the order of G. So the number of p Sylow subgroup itself also divides the order of G. This is one thing, and the number is precisely equal to this. However, something else can also be said about this number. So the proof of this we will see in the exercises. And now next, the last result in this section is the third part of Sylow's theorem, that besides this, something else can also be said about this number. And this is Theorem 212.3. This is the third part of Sylow's theorem. What this one says is this: let G be a finite group and P be a prime. You may be wondering why I am starting these statements like this instead of how it is given directly in the book, where immediately the conclusion itself is given. That's because this is how it should go formally. Formally, every time you write a theorem, these things should come first. The hypothesis, that is what is given to you, and then only you write the conclusion. When we are discussing about these things, then of course we can write somewhat casually, but that is not good always. Then the number of Sylow subgroups of G is of the form 1 plus Kp, where you can understand that K is a non-negative integer. First of all, when we say that some integer has this kind of form or that kind of form, although usually it's not mentioned what that other number is, but it is an integer. But because here we are talking about number of elements, so K cannot be negative. K is a non-negative integer. That is there in the background. We won't say it explicitly. Okay. So the number of Sylow subgroup, besides being the index of the normalizer of any Sylow subgroup, as we have seen just now in that lemma, and besides being a divisor of the order of G, is also of this form 1 plus Kp for some non-negative integer P. Now the proof of this, of course, we are going to see, but not today. Okay, we will see it in the next video. Instead, let us now complete the section by discussing the two applications of the Sylow's theorem and its two other parts. How we can use these things to say non-trivial things about finite groups. So two applications are given. One of them is to the groups of this order. Say you have a finite group whose order is 11 square times 13 square. Can we say something about this group, something non-trivial about this group, using the different parts of Sylow's theorem? Let's see. So what we do immediately is we look at the number of 11 Sylow subgroups of G. Is by this theorem, this last theorem, is of this form 1 plus 11k. Okay, but by the previous lemma, the lemma before this one, this number at the same time also has to divide the order of G. That is, we must have this. Now you can clearly see that 1 plus 11k is relatively prime to 11 square. They have GCD 1. GCD, well, in Herstein's text, we do not write GCD explicitly. Instead, we write a notation like this. Okay, this means GCD, and if you enclose two such integers within square brackets, that means LCM. Since this is equal to 1, Euclid's lemma gives us this, that the number of 11 Sylow subgroups has to divide 13 square. Now one can see a few first values of k. Say you take k equal to 0, k equal to 1, and so on. By doing so, you will quickly see that only one such number divides 13 square, and it's rather easy to see because 13 square has only 3 positive divisors, 1, 13 and 13 square itself. And the only option of this kind of division is that 1 plus 11k has to be equal to 1, which of course is when k is 0. So this means that there is precisely one 11 Sylow subgroup in G. Only one 11 Sylow subgroup. Let us call it A, capital A, in G. Now the best thing about Sylow's theorem is that it's almost like an arsenal. You have many things in it that you can use, many weapons. It's not a single result, but it can be viewed as a collection of results. So this much we have been able to say. But then something else also can be said about this A. This uniqueness further tells us that A is normal. Why? Because you see, if you take now any element of G and form the conjugate of A by this G, then what do you get? Since this A is an 11 Sylow subgroup, we know that its order is 121. Now, what can we say about the order of this this is also going to be a subgroup of G, right? We already know that when we take the conjugate of a subgroup, that is also a subgroup. And if the original group is finite, then the conjugate also has the same order. That means this conjugate is also an 11 Sylow subgroup because it has the same order. But then by uniqueness, they must be the same. But this precisely tells us that A is normal in G. If you run this argument similarly by replacing 11 by 13, that is, instead of looking at how many 11 Sylow subgroups are there, if you look at how many 13 Sylow subgroups are there, you will come to the same conclusion. Same means similar conclusion, that there is only one 13 Sylow subgroup in G, which also, because of this kind of argument, is normal. G has a unique 13 Sylow subgroup. Let us call it B. which is normal. It seems like we have been able to say quite a few things about G, but we can take it even further than this. Now you see one very nice thing about these groups A and B. You see, what is the order of A? Order of A is 11 square, and we already know from a previous result that any group whose order is the square of a prime is abelian. So that means both A and B are abelian. The order of B is also some prime square. Further, these are abelian. But something else is also true. Now, using the abelianness of these two and normality and the fact that their orders are relatively prime, we can now conclude that G itself has to be abelian. How? Let's see. Let A be any element in A and B be any element in B. Then A be A inverse B inverse. Let's consider this element, this kind of element. This belongs to both A and B. And that fact now we will see is a consequence of their normality. This belongs to A. Why? You see, you view this product as the product of A and this element B, A inverse, B inverse. Since A is coming from A inverse also comes from A. And because capital A is normal in G, so B, A inverse, B inverse is in capital A. That normality gives us that. So the product of this element in capital A and A in capital A must be in capital A. Similarly, the element also belongs to B. Why? Because capital B is also normal in G and small b is coming from capital B. So A, B, A inverse, this much belongs to B. And B inverse also belongs to B. So their product also belongs to B. However, what kind of group is A intersection B? Because this has to divide the order of A as well as the order of B, because it's a subgroup of both of them by Lagrange's theorem, and these two numbers are relatively prime. So this has to be 1, there is no other choice. That means this intersection is trivial, which means that AB, A inverse, B inverse has to be the identity element, from which you clearly see that AB must be equal to BA. In fact, we could have recalled one previous exercise in which we did just this. Okay, if you take two normal subgroups which intersect trivially, then every element of one of them commutes with every element of the other. Okay, but it does not hurt to see exactly why this happens. So now the elements in A commute among themselves because A is abelian, and so do the elements in B because B is abelian, and the elements in A and B also commute with one another. So that is why any element of G commutes with any other element of G. Hence, G is abelian. So this is our final conclusion. So that's how, you can of course see that these things have been cherry picked so that we can say so much. It's not always going to be like this, that we will be able to say something definitive about every finite group using only Sylow's theorem and its parts. No, that is not going to happen, but this example at least shows us that we can say many things. Okay, in many cases we will be able to say many things. So any group of order 11 square plus times 13 square is abelian. There is no non-abelian group of that order, and there is one more. Say now that the order of our group is 72, which turns out to be 2 cube times 3 square, 8 times 9. Alright, so now in this case, also are we able to say some things using Sylow's theorem? Yes, we can. Let us see how many 3 Sylow subgroups are there. Now that we have seen how to argue, we can be a little sketchy. The number of 3 Sylow subgroups is of the form 1 plus 3k. We already know that. And we also know that it has to divide the order of G. And due to the fact that 1 plus 3k is relatively prime to 3, it has to divide actually 8, that is this part of the number. Now, unlike the previous case, here we do not get only one option, that is 1 plus 3k is not now necessarily equal to 1, there is another option also, and this number has been called P by the author. Okay, so the possibilities in this case are t equal to 1 and t equal to 4. Now by arguing just like that one, this previous example, if t is 1, then there is only one 3 Sylow subgroup, and that subgroup of course will have order 3 squared, that is 9. And due to the uniqueness, this 3 Sylow subgroup will be a normal subgroup in G. That means there is a normal subgroup in G whose order is 9. So obviously this subgroup is non-trivial. So in this case, G has a non-trivial normal subgroup. However, we cannot have the same we cannot immediately conclude the same thing from t equal to 4, because in that case the Sylow subgroup is not normal. Okay. So what happens if t is equal to 4? In that case, instead of invoking the parts of Sylow's theorem, let us invoke that lemma which tells us the exact number of 3 Sylow subgroups. That number by that lemma is the index of the normalizer of any 3 Sylow subgroup. Suppose that P is a 3 Sylow subgroup. So now we are under this situation. So there are, that there are 3 more besides P, but that is not our concern. Our concern now is this. By that lemma, we now know that the number of 3 Sylow subgroups is this. Okay, the index of the normalizer of P. However, this is 4. Alright. So we are now looking at a subgroup of G whose index is 4. Okay. Now you go back to one result from the 9th section. That section where we have Cayley's theorem. Do you remember that in Cayley's theorem, how we proved that theorem? What is Cayley's theorem? Cayley's theorem tells us that any group can be embedded inside a permutation group. That is, for any G, there exists some set S such that G can be embedded inside A of S. That is, you will find a subgroup of A of S which is isomorphic to G. And in the original proof of Cayley's theorem, we considered the set of elements in G itself as that set S, which, however, although it gave us the proof, it had the disadvantage that our group got lost inside that very big A of S. Because if our group G is finite and has n elements, then A of S is large compared to that, right? It has n factorial elements. In order to what can I say, tame the situation, we wanted a somewhat smaller S, and in trying to do so, we came across one result which itself has some consequences. One of those consequences will be used here. Now, what we need to observe here is that what is the factorial of this number? This is 4 factorial, that means 24. And what is the order of the group? This is 72, which does not divide 4 factorial. So here we can recall one thing, that if G is a group having a proper subgroup H such that G is a group and G is a finite group, the order of G does not divide the factorial of the index of H, then H has a non-trivial normal subgroup of G. This was the result, and it was precisely lemma 291. We can use that here now. Because of this thing, by lemma 291, so in our case that H is n of P. How do we know that n of P is a proper subgroup of G? Because otherwise this index will be 1. No, so that's how we know this. So we can apply this lemma. This contains a non-trivial normal subgroup. Not just any subgroup, but normal subgroup of G, and you can also say of order at least 3. I am not going to exactly elaborate on this, how it is that the order is at least 3. But the main focus is that it's a non-trivial normal subgroup of G. So in this case also, in spite of having 3 Sylow subgroups, 4 number of 3 Sylow subgroups and not a unique 3 Sylow subgroup, still you are ending up concluding that G has a non-trivial normal subgroup. So that is the same conclusion as the previous case. And this is why any group of order 7 to 2 must have a non-trivial normal subgroup. And so no group of order 7 to 2 is simple. Simple groups do not have non-trivial normal subgroups. So this is the non-simplicity of any group of order 72. So they will have non-trivial homomorphisms also going from them, because you can choose that non-trivial normal subgroup as the kernel. So this is where the section ends. Of course, we still have to see the proof of that last theorem. We will do that in the next video. But that's just it for tonight. And our next upload is this, what is the date today? Today is Tuesday, Wednesday, Thursday. Okay, so see you on Thursday with, what the hell, I'm forgetting everything. What do we do on Thursdays? Is it, no, it's not calculus, it's that linear transformations. Okay, so see you with that on Thursday. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.